Example 5.4 gives us two functions, function f, where we're getting the full function definition, and function g, also giving us the full function definition. And we're being asked to define four new functions, one with the sum, f plus g, the other with subtraction, f minus g, product, f times g, and then the quotient, f divided by g. So one of the things that I like about having this full function definition is that I automatically get the domain for free. What I'm circling there is the domain for f, and then what I'll circle now is the domain for g. So if we think about the number line, and if I was to graph or illustrate each of these domains, well, they're both the exact same domain. So when you graph them and put them on the same number line, they're just going to be one on top of the other. So when we start thinking about the intersection of these two domains, well, the intersection is just going to be everything that we already have here. So the domain conversation is actually kind of short. There's not a whole lot of calculating that really needs to go on if you think about the fact that these two domains are identical already. So the domain of f intersected with the domain of g is just going to be negative infinity to negative 3 union negative 3 to 3 union 3 to infinity. So with the exception of the quotient, we have the domain for f plus g, f minus g, and f times g already done. So let's work on the equations. Let's start with f of x plus g of x. So this will be very similar to the last example that we did, 5.3b, where we have fractions. However, these fractions are going to be a little bit nicer than the last because we already have a common denominator. So if you already have a common denominator, then you can go straight to the combining of like terms phase. So this will be 9x minus 1 all divided by x squared minus 9. That'll be done. We'll do the same thing for f of x minus g of x. Swap out the addition for a subtraction operation. And it's important that even though we don't usually write the parentheses when we're dealing with the fractions like this, it is important to know that this subtraction applies to the 4x and it also applies to that negative 2 there, or that subtraction of 2. So when you start combining like terms, be careful with that. So it's going to be 5x minus 4x gives us x, and then 1 minus negative 2 to give us plus 3, all divided by x squared minus 9. So I do expect you to be familiar with some factoring techniques coming into this class. So here's an opportunity for us to see a factoring technique. We have x squared minus 9 in the denominator, and x squared minus 9 will factor into x minus 3 times x plus 3. So if you're a little rusty on your factoring, let me write this down. This is called the difference of two squares. So you can use that as a reference to be able to go back and look up more information on that particular factoring technique. But what I want you to get out of this is that after the factoring is done, you'll notice that we have common factors in x plus 3. So that means that our expression now becomes 1 over x minus 3. Now, x minus 3, which is what we still have here in the denominator, is going to tell us that x is not allowed to be 3. So I can look at the equation and I can figure that out. But when I canceled out the x plus 3's, x plus 3 in the denominator tells me that x is not supposed to be negative 3 as well. And so I lose the ability to be able to recognize that once I cancel out the factors. And I don't want to lose that. So I have to put an extra statement here, comma, x cannot be negative 3 as well. So I have to make sure that that's there, just to remind myself of the original domain that we were working with. So now let's go into the product. So we'll take a look at f of x times g of x. So we are going to be multiplying two fractions together. And multiplying with fractions is one of the easier operations to do with fractions, because all we have to do is multiply across the top and multiply across the bottom. And we are very interested in leaving things in factored form if possible. So this is perfect for that, because then I can just write this, 5x plus 1 times 4x minus 2, and it's in factored form. I don't have to worry about distributing it out, because then it would not be in factored form any longer. And then for the denominator, same idea, x squared minus 9 times x squared minus 9. But what I'll notice about the denominator is that I have the exact same factor twice. So in other words, it's repeated multiplication. Well, repeated multiplication is what exponents are. So we can take this a step further. I'm still not going to do anything with the numerator, and I won't. And then I'll just take the denominator and write it as x squared minus 9 squared. So then we're done with the product. So the only thing left is the quotient. So I'm going to do that right here to the right of my product. So f of x divided by g of x. And with this one, we're going to have a fraction divided by another fraction. And this has a name. This is called a complex fraction. Anytime you have a fraction within a fraction, it's called a complex fraction. And the nice thing about this is that I'm not going to ask you to divide by a fraction. Instead, we're going to use a property that allows us to be able to turn this into a multiplication. So we're going to leave the first fraction, 5x plus 1 over x squared minus 9. We're not going to do anything with that. We're going to change the quotient into a product. And in order to do that, I can't just do that for free. In order to do that, I'm then going to switch the fraction that I have into its reciprocal. So x squared minus 9 over 4x minus 2. So I keep the original numerator, I change the operation, and then I flip or reciprocate the denominator. Now the cool thing about this is that now we can have x squared minus 9 as a common factor in top and bottom to cancel out. So then our statement just reads 5x plus 1 over 4x minus 2. But I have a similar concern that I did on the subtraction. So when I canceled out the x squared minus 9's, I canceled out the fact that x cannot be plus or minus 3. Because when I look at my equation just has 4x minus 2 in the denominator. It doesn't have x squared minus 9 anymore. So when I take 4x minus 2 and have it not be 0, that means 4x cannot be 2, therefore x cannot be 1/2. It doesn't say anything about plus or minus 3. So I would want to go back and make a notation here that x can also not be plus or minus 3. So let me reiterate that. Just because you cancel out the factors algebraically does not mean that it cancels out the domain restriction that's associated with that. So the quotient is actually going to have 3 domain restrictions: positive 3, negative 3, and then we just calculated here in red 1/2. So it's the only one that has to have an extra consideration for its domain beyond what we originally calculated. So now I would like to write out the function definitions. We have all the equations. So for our function definitions, let me give ourselves a little bit of room here. We'll start with f plus g. We calculated the domain previously, so we'll copy that down again. That is what maps to all real numbers by the equation f plus g of x is equal to 9x minus 1 over x squared minus 9. So there is our f plus g definition. Let's do this for f minus g. Same domain, mapping to real numbers, given by f minus g of x is equal to 1 over x minus 3. And I don't have to write down the x cannot equal negative 3 because we already have that notated in the domain right here. So that's already taken care of there, so we don't have to write it down again. If you do write it down, it certainly isn't going to hurt anything. It just becomes a little redundant. Now let's go to the product, fg. The product will also have the same domain, which is going to map to real numbers, given by the equation fg of x is equal to 5x plus 1 times 4x minus 2, all divided by x squared minus 9 squared. And then our last definition will be for f divided by g. Now f divided by g is not going to be identical in its domain. It has to have that extra consideration of taking out 1/2. So its domain will look like this: negative infinity to negative 3, union negative 3 to 1/2, union 1/2 to 3, union 3 to infinity. And that's the domain that will map to real numbers, given by the equation f divided by g of x is equal to 5x plus 1 divided by 4x minus 2. And I'll try to box all that in. That represents the solution here.